everybody. I'm very excited today to introduce Stuart, Professor Stuart Firestein here. So Stuart teaches neuroscience, and he is the chair of the biology department at Columbia. And so he spends most of his time studying olfactory systems, so the sense of smell. And you might wonder why we're having a colloquium about the sense of smell. No, today he's going to tell us everything about ignorance, doubt, uncertainty, and failure. All concepts I'm very familiar with. So, Stuart.
Thank you. It's a great pleasure to be here. I have to say thanks for the introduction. I should point out, to be accurate, I'm the former chair of the Department of Biological Sciences, the word former being perhaps the most important word you can put in front of chair that I can think of. So I'm very happy to be the former chair now. So this talk today is a little bit of a hodgepodge, I have to say, because in this odd way, I've actually given talks about this subject to some extent at churches, synagogues, as well as schools and institutions. And this is actually the first time I feel like I'm actually preaching to the choir in an odd way. So, I mean, I don't think I'm going to say anything today that you don't already know in some way. But what I think is extremely important is that we fail often to make it explicit, and that there are dangers associated with not being explicit about the process by which science occurs. And so some of the things I'm going to point out, and I think you'll just nod your head and go, yeah, of course I know that. But then I'd like to sort of challenge you to think about how we use that implicit sense of how science goes. So, all right, so I am going to talk about ignorance, doubt, uncertainty, and failure, which could lead to some sort of existential despair, but in this cute graphic here, in science, I'm going to give it the rosier picture, if you will, and then point out why I think this is actually the basis of why science is so successful. And science is remarkably successful. You're probably, many of you, familiar with this paper by Eugene Wigner, a physicist, mathematician. This was a very popular paper at one time, this whole idea of the unreasonable effectiveness mathematics in the natural sciences. I'm not going to read over all this, but basically what he pointed out was how unexpected it is really that mathematics, developed for pure reasons in many cases, should turn out to be so effective at describing the physical universe. And this paper then spawned a whole series of papers, for those of you who may follow this, about the unreasonable success of this and that and the other thing, mostly in science. And indeed, it's an active area of inquiry in the philosophy of science. Now, why is science so successful? I mean, what gives it its success? So I don't have an answer for that exactly, but I'm going to suggest some things that I think are important. This is an anonymous and old saying that's become a favorite of mine because I think it's a particularly apt description of how science goes, which says it's very difficult to find a black cat in a dark room, especially when there is no cat, which seems to me to be the perfect description of science. I mean, this is kind of what we really do. We venture into very dark rooms and bumble around, and there's some report of a cat in the area. It may be reliable, it may not be, and we feel around for this cat and we do what we can to find it. Now, I think the interesting thing about this is that it's a very different kind of attitude than I think the public in general has about science, which I think generally is taught to them or promulgated in some way as being a sort of a brotherhood with a set of rules, the scientific method, and that we all adhere to this sort of methodology, this recipe for doing science, and we put stuff into the thing and crank the crank and out come the data and whatever it is. But I think we all know that actually it's more like this. And in fact, it's probably more like that. So, but this is something we never let on to in some odd way until you get fairly advanced in things. So, this was first brought home to me, I suppose, being at Columbia in a dual role, which many of you are in as well, I'm sure, of running a laboratory and teaching undergraduates as well. Or graduates for them, or this is undergraduates. So I run a laboratory, as Rafaela pointed out, and, you know, in the lab, talking with graduate students and postdocs, thinking of experiments about figuring out how the sense of smell works, and then what that means about how other parts of the brain work, and so forth and so on. It's great, right? It gets you in early, and it keeps you there late, and it makes life worth living in a way. It's interesting, it's challenging, and it's exhilarating. And I'm thrilled to be able to do it, as I'm sure all of you are as well. Then I also teach a course called Cell and Molecular Neuroscience 1. This is a course for biology majors. Most of them are pre-med. It's a big course. It's 25 lectures, and organizing this course is challenging and interesting, but it's not, I would say, exhilarating. And I guess that's really the question as to why that's the case. Why is the way we pursue science so different from the way science is perceived? So this course, for example, uses this gigantic textbook, Principles of Neuroscience, by three eminent Columbia neuroscientists, one of whom's passed away recently, Jimmy Schwartz. But anyway, it's a big book, 1,414 pages. Comes in at a whopping hernia-inducing 7.5 pounds. Just to put this in some perspective, 7.5 pounds is about twice the weight of a normal brain. That can't be right? Book on the brain weighs twice as much as a brain. So it became clear to me after some time that by the end of this course, by the end of my 25 fact-filled lectures and reading this book, students must have had two ideas about neuroscience, both of which are terribly, terribly wrong. One idea is we must pretty much know everything there is to know because it's really quite a pile of facts, and that's clearly not the case. And the second thing is that what neuroscientists or any scientists do is they find crap out and they put it in big books, and then they ask people to memorize this stuff for a test, right? And that's kind of the scientific method, if you will. No, that's not true either. I mean, none of those things are true. And when I go to a conference, when you go to conferences, we don't sit around and talk with each other about what we know. We go to the bar, we get a beer, and we talk about what we don't know and what we're going to do about it and how we should get to know it and what's more important to know than or less important to know. I mean, these are the kind of arguments you have or the discussions you have. Sometimes they're just bull sessions, and sometimes they're called grant proposals, but it's the same basic thing in the end, right? So that was the issue, and I came across this quote, which was, I think, caught it really. It's from Marie Curie, a letter to her brother after receiving her second graduate degree. So it's not like she's not very well educated, but what she's interested in is not what has been done. One can only see what remains to be done. And I think that's the issue that we don't talk about enough, the so-called ignorance, what remains to be done, which is what we spend all of our days doing. I'm always fond of pointing out, some of you may have heard me point this out before, but I love this picture of Professor Curie because I'm convinced that glow behind her is not a photographic effect. It's actually like the real thing, you know. Her papers, I understand, are to this day maintained at the Bibliothèque Française in a basement room that's lead-lined, concrete block room, lead-lined, and if you're a scholar and want to get to her notebooks, you have to wear a radiation suit. Crazy. So there are a lot of facts. I mean, we all know about the scientific literature, you know, this ridiculous numbers, 1.6 million papers in 2012. It grows at 2.5%. So, you know, there's a kind of an exponential growth. And this leads too easily, in my opinion, to the accumulation model of science. I mean, nobody reads all these papers. Nobody could possibly keep up with it. And we know that it's not just a question of accumulating more and more facts. Not to say that the facts are not important, but to sort of borrow from Pascal, I think, who first said something like this, that a house is certainly made of stones, but it's more than just a pile of stones. And in the same way, science is certainly more than a pile of facts. So the first thing I think is important to do is to disabuse people. And I don't think I have to do this with you, but I'm going to go through it with you so you can disabuse some other people of sort of common models of science that I think are distortions and potentially dangerous ones. So the first most common model that I know of is everybody thinks what we're doing is patiently piecing together some puzzle. We're all picking up little bits of a puzzle and finding a place for them, and we're putting this big puzzle together, and that's what the scientific activity is about. But I would say, number one, with puzzles, the manufacturer has guaranteed you a solution, right? Which is not really the case with the universe, it seems to me. I mean, whether or not there's a manufacturer is an issue, but certainly if there is one, there doesn't seem to be any guarantee of a solution. And so I don't think that's the case, and I don't think it's the kind of thing that we'll necessarily get to the end of, or that we're anywhere near getting to the end of. So it's not somehow a useful model, it seems to me. And the other one is this sort of iceberg thing, you know, where only 10%, well, you have dark matter, I guess, but it kind of works for you. It's the same idea. But, you know, that only 10% or 5% of the whole thing is visible and most of it's hidden. But there's this notion that it's a thing and you could get to it somehow or another. You could figure it all out at some point. It's not a process. It's not a verb. It's a noun. It's an object, as it were. And I don't think that's the case. I mean, with the iceberg, you could finally get to know about it all, or you could wait for it to melt, which is what it's doing these days, right? So I don't think either of those things work. I'm sorry for the graphic business here, but I think it's closer to this idea of kind of ripples on a pond. I mean, I have a couple of models of this, and other people have come up with this too, that if you think of the ripples on a pond, if you think of the sort of the knowledge being what's in the middle and all this stuff out here being the unknown, the ignorance or whatever, well, as the knowledge base grows, so does the circumference that's in touch with all that ignorance around it, more graphically, if you will, or geometrically, right? So there's knowledge in the middle, the circumference, and as that grows in the darkness of ignorance, then the circumference increases by 6 times the radius. And with a sphere, it's, even more extreme. I don't have to go through this. Oh, sorry. I will just go through this with you, but, it's with the radius squared. So the idea is that as knowledge grows, so somehow or another does the circumference of that knowledge, the shape of that knowledge that's in touch with ignorance. Our ignorance grows kind of along with it. So I think it's typical to think from an educational point of view that we start out in ignorance and we learn stuff and then we become knowledgeable. But I think the arrow could just as profitably go the other way, that the trick really is that when you gain knowledge, the purpose of that knowledge is not to put it in books, is not to stack it away, not to accumulate it, but to ask better questions. That the purpose of learning anything is typically to frame a better, more sophisticated question. So maybe instead of ignorance, you could put questions there. I like to tell the story of I.I. Robbie, who you guys know more about than I do, of course. He was a professor of physics at Columbia, and Robbie was fond of telling this story. I never heard him tell it personally, but he told it to colleagues of mine anyway, who retold it to me. And he used to claim that when he was a child growing up in the Lower East Side of New York, he'd come home from school with his friends, and all of his friends' mothers would say to their kids, so what did you learn today in school and all that? But Robbie's mother said, so Isidore, did you ask any good questions today? And that to me is the whole difference. I mean, I think Mrs. Robbie had the right idea, and Izzy got the Nobel Prize, not his friends. So I think that's the idea, this notion of questions. All right, so I use the word ignorance, of course, here to be purposely provocative, and I don't mean stupidity, I don't mean a callow indifference to fact or being uninterested in fact. I mean a certain kind of ignorance that this guy, I think, says best. So this is James Clerk Maxwell, in my opinion, I guess maybe the greatest physicist between Newton and Einstein. I'm sure you all have your favorite, but to me he would be one. So that's Maxwell, who said thoroughly conscious ignorance is the prelude to every real advance in science. And so that's the kind of ignorance that I mean, this notion of thoroughly conscious ignorance. So to go along with ignorance, because I'm also going to talk about failure, I'll give you a quote from Benjamin Franklin, America's, I suppose, first scientist, who says, perhaps the history of errors of mankind, all things considered, by errors I take it to mean failures, is more valuable and interesting than that of their discoveries. Truth is uniform and narrow, but error is endlessly diversified. I also fond of calling this the Anna Karenina principle after Tolstoy, who when asked why he always wrote about unhappy families, said, well, happy families are all happy in the same way, but unhappy families are unhappy in a myriad of ways, so they're much more interesting. I'll give you a final quote. I'm sorry, I like to use quotes. It's not that I'm looking for authority or anything like that. I think, though, that first of all, dead people shouldn't be necessarily left out of the conversation just because they're dead. And also I think it's important to recognize that this conversation, as it were, has been going on for some time and will continue to go on, and it's up to us to join it, but we're not starting it. We're probably not going to finish it. Anyway, this was a toast that George Bernard Shaw delivered at a dinner in honor of Einstein, no less, in which he said, science is always wrong. It never solves a problem without creating 10 more, which I find kind of glorious and good for your job. As it turns out, he apparently cribbed this from Immanuel Kant, who first coined the idea of the principle of question propagation, the notion that every answer begets a fresh question. And Shaw just increased it by an order of magnitude, which I think is a Shavian kind of thing to do. But he's probably right. It probably is 10 more. So I'm going to give you an example, a very quick example from my own field of how this kind of thing I think operates. And I'm sure you have examples from your work as well. So in 1991, now just a little over 24 years ago, in April of 1991, this landmark paper was published by Linda Buck and Richard Axel, both of whom were at Columbia's medical school at the time, titled A Novel Multi-Gene Family, encode odorant receptors, and the subtitle is really important, A Molecular Basis for Odor Recognition. So this was indeed a landmark paper. Buck and Axel were awarded a Nobel Prize in Physiology for this discovery in 2004. Well, a bunch of unexpected findings, but the most remarkable of them was that they uncovered about 1,000 genes in the typical mammalian genome that encoded for odor receptors. I mean, about 5% of your genome. We think there are about 25,000 genes in the mammalian genome, so 5% of your genes are encoding odor receptors. I mean, that's crazy. Who would have thought that? But here's an interesting thing about the history of the field. So I went off and did just a very quick search using the keywords odor or odor receptor. So in the 30 years before 1991, between 1961 and 1991, there were 300, not quite 300 papers that I found using the word odor or odor receptor, published at the rate of about 10 a year. Then in 91, this paper came out. 4 years later, or 5 years later, in 1996, there were 406 new papers in the literature dealing with odors and odor receptors, now at a rate of some 80 per year, an eightfold increase. And by 2012 or 13, I think this data is actually, there were then 4,000 papers in the literature that had been newly added and now being published at the rate of almost 200 per year. So the point is this landmark paper, which solved a big problem. I mean, it told us a great deal about the molecular basis of encoding odors and the olfactory system, nonetheless actually spawned a huge increase in activity in this area. So it didn't settle it, it didn't stop it, it did the best thing a scientific paper can do. It increased interest and spawned a whole slew of new questions that we would never have thought to ask before, never have thought to attack before, wouldn't have had the tools to attack. So to me, that's the best kind of situation. So this is a sort of banging around a little bit now, just trying to introduce as many ideas as I can that we can talk about afterwards. So if we think that the search at science, and I think it's true of art, is a search for better ignorance, I think there's an interesting term called negative capability that was coined by the poet John Keats. This also in a letter to his brother. Apparently it's a good idea to write letters to your brother. I'm not sure why, but anyway, he talked about negative capability, which is when a man is capable of being in uncertainties, mysteries, and doubts without any irritable reaching after fact and reason. He considered this to be the ideal creative state for the literary mind, but I think it's the ideal creative state, period. This notion that you can rest with mystery, that you can rest with uncertainty and with doubt, and this, I don't know about this irritable reaching after fact and reason. Of course you reach, but it doesn't have to be irritable or neurotic, at least I suppose. This was sort of restated for the scientists, although I'm not sure he meant it this way, by Erwin Schrodinger, who knows a little something about cats, or doesn't. I'm not really sure which it is. Did you see that great New Yorker cartoon that came out recently? There was a cartoon in the New Yorker, guy sitting in a veterinary office, there's like dogs and cats on the floor, and the vet standing there with a clipboard and saying, well, Mr. Schrodinger, about your cat, I have good news and bad news. This is perfect. So anyway, what Schrodinger said was, in an honest search for knowledge, you quite often have to abide by ignorance for an indefinite period. And I think that's an extremely important thing to tell students and the public and all sorts of funding agencies and things like that, that this is critical to the process. Now, this guy doesn't really belong with all the others, but he said this thing, which he became famous for, about the Iraq War, about things that we don't know, known unknowns, and so forth. And then he was worried about these unknown unknowns, the things we don't even know we don't know. So that's yet a further step deeper into the mysteries of ignorance. Other people have said this before him, but he's the most recent and notorious to have said it, so I thought I'd use him. So how do we know about unknown unknowns? That is, the even deeper bits of ignorance, not just what we don't know, but what we don't even know we don't know. So I think that's where failure comes in, and that's where failure in science is so different than failure in so many other areas. So there's a lot of stuff out there on failure. If you want to go to the bookstore, the self-help or the business section is loaded with books on failure and how good it is. And since we're in commencement season now, you always hear commencement speeches about embracing failure and all this other crap. which it mostly is. Because really, people are not talking about the kind of failure that I think we understand as scientists, and it's quite different than this notion of, well, you fail in order to succeed, or failure teaches you perseverance, it's character building, all this other stuff, all of which is true and of use. But in science, we don't just fail to get to another place, we fail to fail some more. I mean, failure is an integral part of our process. If you're not failing enough, you're really not probably doing anything very interesting, it seems to me. And one of the ways we learn about the stuff we don't know is through failure, right? Because, so you don't know something, so you do an experiment. And then you get a result that's not the result you expected at all. And now you realize, well, I don't even know what I don't know about this, right? I mean, so I think it gets you even deeper into the thing. So quote of mine that I'm very fond of, Enrico Fermi apparently used to say to his students that if you perform an experiment and it proves the hypothesis, you've made a measurement. If you perform an experiment and doesn't prove the hypothesis, you've made a discovery. And I think that's very good advice. A second one of these, one of my favorite Isaac Asimov phrases, the most exciting phrase to hear in science is not eureka, but, oh, that's strange, or that's funny, right? I mean, that's what we really want to see when we see a piece of data. It's not, wow, there it is, go home, let's get out of here. It's, wow, that doesn't make sense. What's going on here? There must be something deeper that we don't understand yet, that we could understand better. So we gain new knowledge through failures. I have to use an Einstein quote in here somewhere. So he said, if we knew what we were doing, of course, it would not be called research, would it? And that's pretty simple and clearer, but sometimes we lose track of that, you know. All right, so failure. So here are a couple of other quotes about failure that I think I'm just trying to nail down this idea of failure in science. So Gertrude Stein wonderfully said, a real failure does not need an excuse. It's an end in itself. I like this idea of it being an end in itself, not just a means to something else, but actually a failure can be an end in itself. It takes a while to think about that and get a hold of it, but I think one can work that way. We'll talk about that some more in a minute. I didn't actually want this slide. I wanted a different slide, but okay. Forget this one for the moment. I think there's one after this that's more interesting. Yeah, okay. Let's see. Hold on. Sorry. Okay. Here's another failure quote. Ever tried, ever failed. No matter, try again, fail better. Fail better. That's really curious, isn't it? This is, of course, you might imagine, since it's so enigmatic, from Samuel Beckett. But you know, the first part of it sounds like one of these sort of self-help things. Okay, tried, failed, get up, try again, fail again, try again, blah, 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 blah. And then he comes up with this idea of failing better. I mean, the notion of failing better, not just failing to succeed, but failing in a better way, I think is really worth thinking about. And then one from Alan Turing, if a machine is expected to be infallible, it cannot also be intelligent. So I think it's from things like ignorance and failure that come creativity, innovation, new ideas, and so forth, and approaches. All right, so one could ask a question, if failure is such a great thing, how much of it should there be? And I think this is an area that we regularly underestimate. I mean, clearly, 100% failure is probably not a great idea. So we can start there and say, well, better not to fail the whole time. Although there are those of us, I guess, who do that, and some who get away with it even. But it's probably not the best bet. So how much? So we can look around at a couple places and see. I have two examples here. I have other ones we could talk about too. So in the animal kingdom, if you study predator-prey relations, these are all critters that are considered to be at the top of the food chain, as it were. These are the kings of whatever niche it is they're inhabiting, right? And the most dangerous creatures around. And the idea is that anytime they get a little hungry and feel like a snack, they just go out and bag some poor critter and chomp it up. But actually, that's not the case. So when you actually study carefully predator-prey relations, you find out that these guys are successful in fewer than 7% of their attempts. That's why they're almost always on the hunt, because predators are pretty good at escaping them. And this is, you know, they're working around the edge of the herd on the old and the sick, no less. If you want to have something really young and juicy, you know, then your 7% goes even further down. So they're really only successful 7% of the time, and yet they're the kings of the whatever, you know. I have a baseball metaphor since it's New York and Boston here. I have to go with Ted Williams and Joe DiMaggio, two of the greatest hitters in the history of baseball. One guy played for you, one guy played for us. These are their batting averages, right, which essentially tell you how many times they were successful out of the number of times they were up, more or less. I know it's not perfect. So they played a large number of seasons, had a large number of at-bats, so these statistics are reasonably reliable. And here you are, out of over 7,000 at-bats, or nearly 7,000 at-bats, there are about a few more than 2,000 actual hits, and something like 5,000 times that they were out. So 70% of the time, or more, nearly 70% of the time, they failed. And that's true for baseball players today. If you're a batter and you can manage a 300 average or better, which is a 70% failure rate, you're likely to have a $10 to $14 million a year contract, which ain't bad for failing 70% of the time, it seems to me. So clearly, and so I can give you other examples like evolution itself, which is a huge failure for 99.9% of the species that have ever existed on the face of this planet and are now extinct, which I think you'd have to call a failure in some way or another, at least for them. So clearly you can fail quite a bit. And I think one of the things we don't do is consider how much failure is actually quite acceptable and therefore good. Niels Bohr called an expert a person who's made all the mistakes that can be made in a very narrow field. So he didn't say somebody who succeeded in a very narrow field, but somebody who's made all the mistakes possible in a narrow field. So this is a term that comes up a lot, it seems to me, when you talk about failure and occasionally succeeding and all that. It's this notion of serendipity in science, which I just want to have a short rant on because I think it's overplayed. You know, if you go to the Nobel Prize site and you read the Nobel laureates' description of how they came up with it, 50% of them will tell you, oh, it was kind of serendipity, or it was a bit of an accident, or this or that. And whether that's out of some false sense of humility or really believing that just as easily somebody else could have discovered this as me, which is often the case, it's not really, I think, just a question of luck or accident. So the thing about, and I think this is overplayed a bit, this notion that, well, so much of science is serendipity. In fact, many people use this idea of serendipity as a defense of fundamental or basic research. The idea being, well, we don't really know where applications will come from, so we should just go out and be curious and work on things, all of which I believe, but then they use this idea of serendipity because, look, you never know where it's going to come from, so we just trust in serendipity and then great things happen. But I think what's important to recognize is that, you know, lawyers don't make serendipitous scientific discoveries. Accountants don't make serendipitous scientific discoveries. Scientists do. Because you're working hard on something, and then an unexpected result may appear. Now, if you're clever enough to take advantage of that unexpected result, to take note of it, to accept it, to say, oh, that's a failure, but that's kind of an interesting failure, then it feels to some extent like serendipity. So there's the famous phrase of Louis Pasteur, himself the recipient of quite a bit of serendipity, if you want, but his feeling was, of course, that chance favors the prepared mind. I have a corollary to that. My corollary is failure also favors the prepared mind. So I think that's crucial to be prepared for it because we all know it's going to happen quite a bit, and there's a lot to be gotten out of it. All right, so we have ignorance, which creates doubt and uncertainty, failure. This all sounds pretty bad, right? Could lead to despair. It's miserable. But curiously, it does not. So in science, as in nowhere else, you list those three things, and instead of despair, what we find is, this is where, oh, sorry for the graphic stuff. It's from an earlier talk. That what we really find from these things is a sense of creativity. This is where the creativity in science comes from. This is where there is not a scientific, I don't like the idea of a scientific method. You may have guessed that already. Not that I object to the notion of, you know, hypothesis, observation, manipulation, all that stuff. But I don't like the idea that there's a recipe, as if, oh yeah, it's a, you know, there's a method for this. You just look it up, it's a recipe and all the rest of that. The scientific method kind of falls down when it says, come up with a hypothesis. Really? Well, how do you do that exactly? The scientific method never tells you how to do that. Will you look it up in a catalog somewhere? Is there a book of hypotheses? How about if there are 2 or 3 hypotheses that are equally, I don't know. So it doesn't say anything about that. And I kind of don't like this notion that science is, I don't think that it's not systematic, but that it's not methodical in this uncreative kind of way that it's often portrayed. So, but here's the problem then. So I don't think I've told you anything yet or used a quote on you yet that you don't more or less agree with or are nodding in assent to. But the question is that idea only available to experts? Are we kind of an elite in science because, not intentionally maybe, but because we never allow it to become explicit that this is what we traffic in? That we indeed traffic in ignorance, doubt, uncertainty, and failure, and that's why things are working so well. Here's an example of this. This is a famous story of sorts about Albert Einstein and Einstein Weitzman, first premier of Israel. And they were on an Atlantic crossing together. And on this crossing, Weitzman decided with Einstein that they would sit every day on the deck for 2 hours, and Einstein would explain relativity to Weitzman. And then the trip went on, I guess, for about 10 days or whatever. And Weitzman said at the end, as every day we'd sit on the deck for 2 hours in the morning, and Einstein would explain relativity to me. After 2 weeks, we arrived, and I was convinced that Einstein understood relativity. But this is the problem, right? I mean, Weitzman asked him the wrong question. Weitzman said, okay, so whatever relativity is, that's cool. Maybe you can tell me in a couple of words or something. But what are the new ideas that tells us about? What are the new questions that brings up? And what about this guy Bohr and those characters up there in Copenhagen and their ideas? And I mean, how do what are the questions? And then I think he'd have gotten a real earful from Einstein that would have changed much about the way he thought about the world. So the trick is to ask about the questions, right? So these are the kind of distortions that I think are very common right now in the public mind. And I think in many ways they're our fault, if you will, that we allow these things to go on, that science has a kind of inevitability about it, that it's endless, that we seek truth, which has something to do with certainty, which I don't think is correct, that all we do is produce facts, that it's a lot of these facts, that we write them in books, that scientific discoveries are made by geniuses or geeks, depending who have eureka moments, these heroic narratives that we tell about science, these kind of arc of discovery myths that I don't think do us any good really in the end, because there's no scientific discovery made that way that I'm aware of without tons of work behind it and lots of people behind it. That experiments tend to work and that advances come rapidly because every day you open the paper and there's some new finding announced by some lab, but there are thousands of laboratories all over the world working on problems, and it takes quite a lot of time. And one of the things I think we've lost in science, in our approach to science, is the notion of patience. And this is extremely important for people that fund it, for people that teach it, for people that do it. We need to relearn the notion of patience. And then, of course, this thing about a scientific method. So, all right, so scientific progress generates ignorance, uncertainty, doubt, and failure. But is this a problem? Is this good or bad? I'd say it's good because what's important, I think, is that we should not equate ignorance with stupidity, that uncertainty is not the same thing as unreliability. This is, I think, one of the more egregious areas that we have to worry about, this use of the word uncertainty, because uncertainty, there's a lot of words out there in the common language that don't mean the same thing in that world as it means in the science world, and we're often not explicit about that. So, I mean, you see this in climate change debates and stuff like that now, where scientists will say, well, there's a certain level of uncertainty in this, and then the public means, well, you mean you just don't know, right? And that's not the case. Uncertainty is a quantity that we measure. We understand how to measure uncertainty. We work with uncertainty, and it's a measurable thing, not just some unreliable number somehow or another, or unreliable idea. Doubt is not suspect. It's extremely important. If one doesn't doubt, then, the alternative to doubt is, well, let's not question authority, whether that authority is a political authority or a granting agency authority or Aristotle. Any one of those things doesn't really work. If you don't doubt, if you don't question authority, then if you want certainty, then usually along with certainty come demagogues and dictators, in my opinion. So why we want that, I don't know. And failure does not really mean things are wrong. Failure is just something we haven't seen yet. Failure tells us there's more there to see. So I think the key thing in all this is the idea that unsettled science, which all science is, I think, in most of our opinions, is not the same thing as unsound science. And this is a crucial distinction to make, at least in the public sphere, and I think to our students as well. Speaking of students, I'll go through this quickly. I was actually meant to not include this in the talk, but here it is. So do we teach failure well enough? I'll do this quickly. So I think currently we have what I call the Bulimic Model of teaching science, where we cram a lot of facts down some kids' throats and then they puke it up on some exam, and then they go away to the next unit with no real appreciable gain anywhere. And that can't be working. That can't be right. I mean, we find that in the second or third grade, all the kids love science, the boys and the girls. They want to do cool things. They want to do experiments, they want to look through microscopes, go to the museums. And by the 11th or 12th grade, let alone college, fewer than 5% now apparently claim that they want a career in science or actually want anything to do with science. So we somehow or another have developed this educational machine that's maximally effective at disengaging the most possible people you can imagine from any interest in science. I can't believe that's what we want. But, you know, it's what we have. The geneticists have this phrase, you always get what you select for, but that's a warning. You know, that's not usually a good thing, because it means you don't know what you've selected for, but you'll get it for sure. So, you know, you have to be careful about what you select for, if you will, right? And we're not clearly selecting for the right thing because the outcome doesn't seem to be the one that we want. We can talk about that. So I made a quick list of what I learned as a graduate, and I think what's important about this is that this educational problem, this kind of bulimic approach to education, goes on all the way through undergraduate, even for science majors, let alone, I mean, I don't worry so much about science majors because they're going to go to graduate school and they're going to learn this list of stuff I'm going to show you here, which is more important. I do worry a great deal about undergraduates who are not going to become professional scientists, whose last encounter with science in any kind of a formal way will be some undergraduate science course, much like my neuroscience course, or worse even, because it'll be duller, I think, because it won't be as deep. And that will be it. I mean, they will just find some fact-filled textbook. It's, I mean, you know, and the textbooks we use would be like, I mean, it would be like a literature professor teaching Ulysses with the Cliffs Notes, or Shakespeare with just the plot outlines, because that's what textbooks tend to do, it seems to me. So this is clearly a mistake. So here's what I learned as a graduate student that I think are important. So first of all, the first thing you learn is that questions are more important than the facts. More important than more facts, yes, or more important than facts. That all the stuff you learned is great, but really, as a graduate student, you got to learn how to ask questions. Answers and facts are temporary. Data and hypotheses are all provisional. In science, revision is a victory. It's a critical thing to remember because it ain't true everywhere. Failure happens a lot. Patience is a requirement. Occasionally you get lucky. Hopefully you recognize it. And things don't happen in that linear or narrative way that you read about in papers or textbooks. This arc of discovery notion is a myth. I mean, we all know that scientific papers, as Peter Medawar, immunologists, said, are a total fraud because they're not presented in the order in which the discoveries occurred, or are they a record of the chronological way or even the method by which they occurred. They're just placed in some rational order of how you now want to present those discoveries. That's fine, but we should recognize that it's not a historical document in any way, shape, or form, and that you can't use it to then make your own set of discoveries. And then finally, if there's free food, get there early. I think we all keep that with us for the whole time. But I have to say, I mean, none of these things are part of an undergraduate training in science, even for science majors. I mean, I never heard any of this stuff as an undergraduate. I was never treated to any of these ideas. And so these are the people we're leaving behind, and I think it's a seriously bad idea. So I'm almost at the end here, and then I'd like to have a discussion. So there's Karl Popper, of course, who I guess is the philosopher of failure, and this is another issue that I think dogs us in the political sphere especially, this idea of determining real science versus pseudoscience. So sometimes this is easy to do. This was Popper's real interest in understand that one of his main interests as an early philosopher was how do we tell the difference between real science and pseudoscience. So astronomy and astrology, that's not so hard to figure out. Even chemistry and alchemy, not so hard to figure out. But here's an example for, sorry, hold on. Yes. Used to having a remote, actually. Here's an example that's not so simple, it seems to me. So, well, we're past flu season now, but the flu, which is officially called influenza, from the Italian for influence, because the flu was originally thought to be caused by influence, unseen celestial influences from the moon and the stars, and astrologers would predict these flu epidemics. And so the idea was there were unseen celestial forces at work that would create this disease. That's clearly a crock, right? We know that's not true. But at the same time, I'd like to sit here and tell you that the oceans out there, these tides that you see come back and forth, well, they're caused by unseen celestial influences. Why do you believe that? You know, so it's not always so easy to tell the difference or to make clear the difference between real science and pseudoscience. And if you think that's an old idea, we still have this problem with things like evolution, genetically modified organisms, organic and natural foods versus synthetic things, vaccines and nuclear energy, alternative medicine. I mean, a whole list of crazy things that intelligent people believe. And this is, I have to say, this is not a political, this is not a right wing versus left wing. There's not a blue state, red state thing or anything like that. I mean, there are a whole slew of very liberal thinking, well-educated people that are against genetically modified organisms and crops. Maybe many sitting in this room. But I have to say, you can take that point of view, but I think I've never heard anybody give a really good scientific reason for worrying about them. And in the meantime, there are millions of people in the world starving. So we can be worried about the fact that, you know, some percentage of people out in some red state in a church somewhere don't believe in evolution, but really it just means a couple of thousand kids are getting a crappy education in biology. But when you suspect genetically modified organisms or genetically modified crops as a way to avoid using pesticides and grow more food to feed more people and so forth, well then people are actually dying from that. And one of my favorite statistics, because Europeans are always fond of pointing out that 50% of the people in the U.S. don't believe in evolution, 25% of high school seniors in Europe in a recent poll were asked whether genes only exist in genetically modified organisms and answered yes to that question. That's really bad, I have to tell you. That's much worse than not believing in evolution, which, as I say, only means you get a lousy biology education. But nobody dies from that I'm aware of. So Popper's idea, of course, was falsifiability, that science can be distinguished from pseudoscience because it can be falsified. And anything that can't be falsified can't be true. If you can always work around somehow or another and come up with an explanation. I mean, astrologers never, ever seem to get it wrong, right? They always, somehow or another, get it right. Well, so that can't be real science. But there are problems with that, too. I mean, so the common example is white swans. Till you go to, all swans are white, you know, till you go to Australia and you see it turns out there are black swans. And so that means that the hypothesis is wrong. But ironically, it kind of removes failure from science because there are lots of cases where you can't still make the distinction. So you guys as astronomers in here would know, you know, there's the Neptune problem, which at first you would think should mean that it falsifies Newton's hypotheses, right? Because Neptune was not moving correctly according to Newtonian mechanics. But then it turned out it was because there's a bigger planet behind it, and actually Newton is saved and shown to be even more right. But then there's this other problem with Mercury and its orbit that does not apparently obey, you know, Newtonian principles. But that's true. I mean, it really doesn't obey Newtonian principles. There's an Einsteinian relativity issue there. So it did falsify some piece of Newton in that case. Now, how do you tell those things apart? And of course, there's also the problem of very few hypotheses stand on their own. There's a whole web of data under them and hypotheses under them, and you can't usually just pull one out and say, well, let's get rid of that one and do this other one. So it can be actually problematic. But it does say that failure is a critical part of true science, and that science that only succeeds is likely to be somehow or another false science. So I think it's important for that. All right, so here's my solution to it, and this is what I'd actually like to discuss. And that's the notion of pluralism, which I think we do not, as scientists, do not practice sufficiently. And I don't think we do it intentionally, but I think it's a kind of a creeping monism in science these days. So my hero for pluralism is the philosopher Isaiah Berlin, the English philosopher. And he wrote this little pamphlet once called The Fox and the Hedgehog, in which he borrowed this idea from a Greek poet. The fox knows many things, but the hedgehog knows one big thing. And this book was supposed to be a critique of Tolstoy or something like that, but he used it to sort of classify thinkers. Well, people either think like a fox or think like a hedgehog. They have one big idea, or they have lots of little, you know, many things that they know. And of course, nobody is typically one or the other. But Berlin would in general say foxiness is a better idea than hedgehogginess. And I think as scientists we do both, or should do both. So Berlin eventually came up with this notion not just of pluralism, but value pluralism. Not just relativism or subjectivism or anything goes or whatever, but there are chosen things that go, but many of them, at least more than one, that we shouldn't be overly monistic in our view. So, and quite often, Berlin would point out, there are things that are incommensurable. They're both good, they're both valuable, we like them both, we think they're both right even, but they're incommensurable. I mean, he was mostly a political scientist and political philosopher, so he would probably use an example like liberty and security. We believe that both are important things to run a peaceful society, but they're often in opposition to each other. And so you have to somehow or another learn to live with these incommensurable goods. I think F. Scott Fitzgerald said something like the sign of a true intelligence is to be able to hold two opposing ideas in your mind at the same time and still function. And I think that's kind of what pluralism is. So where does this come up in science? Well, I don't think it really comes up so much at the bench, if you will, where we do tend to be a bit hedgehoggy and for good reasons. I mean, we have an idea and we push through that idea. But other people have other ideas and they can be their own hedgehogs. And part of being the right kind of hedgehog is being foxy enough to let other people do it. But where it really is important is in so much of what we do in science that's not directly at the bench, it's not directly in the laboratory, but has a huge effect on how science happens. So funding, of course, I'm just going to make a bit of a list here. Funding, hiring, promotions and tenure, space and resources, education and curriculum, reviewing, papers, grants, programs, references and recommendations that we write for people, planning and policy, public policy and governance. All of these areas are things that scientists do with, I would say, in many cases, especially as a senior scientist, with half of your time, or sometimes more, unfortunately, whatever the administrators haven't gotten you to do otherwise with your time. But these all speak to the infrastructure of science. And I think they require a very pluralistic view on our part, because if not, we wind up with just one or two strategies that sort of become a fad, and that's what everybody goes off and does. I mean, this happens, I have to say, in biology, and especially in the disease area again and again. I could tell you horror stories about research in Alzheimer's disease, to the point now where drug companies, almost all drug companies, have closed down their research on Alzheimer's disease because they've gotten tired of chasing one fad after another, whether it's A beta protein or tau protein or whatever you've read about or heard about or whatever. I go into hard details with you about it. I mean, you know, all of a sudden somebody makes a discovery, and it's the old Chinese proverb about one dog barks and 100 dogs bark at the sound. And this is a kind of this monistic view, this rushing off in fads one way or the other, rather than having a pluralistic view and maintaining more possibilities. So the Boston historian, I think he's mostly famous for being a Bostonian and a Harvard man, Charles Sanders Peirce, likened science to a cable rather than a chain who's, of course, you know, only as strong as the proverbial weakest link. Peirce said science is like a cable made up of many delicate strands, each one fragile, but one bundled of immense strength. And the critical thing is the loss of a few strands does not weaken the strength of the cable. And so this is the idea of a pluralistic rather than monistic approach to science. So here's my favorite example. This is from a fellow named Ha-Suk Chang, who's a philosopher of science, studied actually as a physicist originally and then moved over to philosophy of science. I think he was at Harvard at one time. I think he got his PhD. No, he got his PhD at Stanford. I don't know. He was at Harvard for a while as a postdoc maybe. He's now at the University of Cambridge as a professor. And he uses this wonderful example of multiple technologies and sciences existing at once, as shown in the GPS device. So, for example, for a GPS device to work, you have to launch a satellite, which you use Newtonian mechanics to do. That satellite has within it an atomic clock based on quantum mechanical principles. But of course, it has to have a relativistic correction for low gravity or it won't be right. And all of this is in the service of giving you a flat Earth map back here. So you have these sort of four technologies, if you will, that work all at once and coexisting quite peacefully and remarkably in a device that we all make great use of. And some of us make nefarious use of, but that's another story altogether. So, all right, let me end with this. This is Francois Jacob is a geneticist who won a Nobel Prize, and I forget when now, and he died at 92 years of age a couple of years ago, not 2 years ago, and this is from New York Times obituary. That's him and his longtime collaborator, Monod, working in a lab with a traditional cigarette. and so forth. You notice up there, that's the way things worked in biology labs especially. I'm still convinced to this day that there are experiments that don't work because there's no nicotine floating around in the air. So, this actually is sort of from a couple of different books that Jacob wrote. So, what mattered more than the answers were the questions and how they were formulated. For the best of cases, the answer led to more questions. I put in the word doubt. It was a system for concocting expectation, a machine for making the future. For me, this world of questions, quote, ignorance, and the provisional, uncertainty, this chase after an answer that was always put off to the next day, failures, all that was euphoric. And here's the great phrase, I lived in the future, which I think is maybe the most you can ask to do. I'll just end it with this poetic thing from James Joyce, mistakes are the portals of discovery, so make mistakes. It's the best way to go. All right, thank you very much. I don't have any more. I could go on, but I'd like to have a discussion.
Time for questions for Stuart, Ari?
So, you drew the landscape very nicely. From my perspective, the issue is really taking risks, and because when you have uncertainty and you're ignorant about the truth, you have to take risks because you don't know where exactly to go. Now, the practical issue is not so much, I mean, we're not just talking philosophy here, the practical issue is for funding agencies.
Yeah.
And how do we allocate funds to researchers such that you maximize the benefits to society, let's say, because it's taxpayers' money. And the unfortunate fact about the US, for example, NSF, if we take a particular example, or NASA, in the case of astronomy, is that, for example, in NASA, you have to forecast what you will discover. In other words, you have to lay what you will do in year 1, year 2, year 3. And based on that, they will decide, or the reviewers will decide whether you should get the funds. That's completely contradictory to this landscape that you were. So what would you recommend as being the best policy for allocating funds?
Well, so it's a tricky question. I mean, I agree, and it's a serious one and one that we have to worry about. But as you know, I mean, both NSF and NIH, which is where I go for funding, they have this remarkable category called high-risk, high-impact grants. So I think 5% or 2.8% now, or some crazy number, of the money given out is for so-called high-risk, high-impact grants. And I'm thinking to myself, really? I mean, why do we need a category like that? So what are the other 95% of the grants? Incremental crap that we don't really care much about? I mean, does that make sense? Why would you even have, I mean, that's what science is high-risk, high-impact, if it's worth anything. So clearly, there's a mistake there. I think, of course, these things only become, they show their threads, they become threadbare when the money gets too small. So, I mean, in the end, I hate to say this, but I think actually a very sensible solution would be to throw more money at it. That if you want to have risk, if you want to include risk and failure in science, which I think you do if you want healthy science, then you have to pay for that. I mean, you pay for risk and you pay for failure. And you do that because it works out, because it's worked out so frickin' well for so many years. It's hard to understand why people don't think it still will. And that doesn't mean you have to fund everything, but I mean, so I know the NIH better than I know NASA or NSF, so I can, but I'm sure the numbers are very similar. At NIH until I would say 10 or 12 years ago, the so-called pay line, which sounds horribly like a gambling casino term, the pay line was about the 28th or 30th percentile, which meant that somewhere around 28, 30% of the grants being submitted were being funded. I think that was fine. I think that's perfectly reasonable. And indeed, there was a tremendous amount of science that went on, and now the pay lines are down as low as 8th and 10th percentile. At that point, my recommendation is if you get a grant, use it to go out and buy lottery tickets, because that's the most likely way you'll get the grant refunded or get more money in the lab, right? So, and actually there are many people thinking about this, and there are people making the sincere suggestion, and they've backed it up with numbers, that the best way to fund might actually be a simple lottery. That we should forget grant proposals and all the rest of that crap. You should put your name into the hat. You have a position at Harvard or here or there, wherever your position is. You run a laboratory, you put your name in a hat, and we fund 30% of them. And every year we pick another 30% out of the hat, and there's a lot of sort of modeling evidence that suggests that it wouldn't change things very much, except it would remove a lot of time-consuming crap that we do.
Venture capitalists.
Yeah.
That's what they do, and
Yeah.
one of them I spoke with just last week, and he said there was a startup that he invested in a lot of money and it failed. And then he went to the person in charge and said, come up with your next idea because I want to invest in you. Nevertheless, so he asked me, how many do you think of the other venture capitalists came to that person? And I thought nobody, but he said everyone.
Yeah, yeah.
Because that's the nature of the game. You have to put money into it.
Yes. Yeah, and you understand what the percentages are, so these demands that are made on. I think part of the problem comes from an overemphasis on applications and applied science and so-called usefulness, which we know we're extremely bad at predicting. I mean, I'm not against applied science. I love drugs, and I love medical drugs. I love medicine when I need it. I like gadgets. I own all the gadgets and everything. I love all that stuff. I love the applications. But clearly you can't, you're not going to keep coming up with just application after application, or it's actually going to become more and more expensive to get to those applications. To wit, the case in Alzheimer's disease, where the drug companies there's not enough basic research in Alzheimer's disease to chase after. I don't want to get too far off on a tangent, but a perfect example of that was the treatment of depression, which was thought to involve serotonin. There's actually very little evidence that serotonin is involved in depression, except that drugs that affect the level of serotonin in your brain, for some people, seem to fix their depression. And so a whole story gets spun out on serotonin and depression, but there's very little basic research, fundamental research, that makes the connection or makes it in a mechanistic, understandable way. And so the drug companies, immediately after having come up with, what's the one? Prozac. Having come up with Prozac, which increases serotonin levels in your synapses and so forth. But it has side effects. So the first thing they thought of, well, let's just go back and design another drug that does the same thing and get rid of the side effects. And that's what they did. And the drug doesn't work. So, that's the problem. It's not just serotonin. It's other things that go along with it. Serotonin is presumably involved, but if you don't do the basic research, you waste it. And they wasted a lot of money on these second generation drugs, which have, $400 million clinical trials and randomized this and all down the drain for nothing, for absolutely nothing, when that money could have gone into fundamental research and actually understood schizophrenia in such a way that we could actually go out and design a drug for it, or depression. So there are lots of examples like that, I'm afraid. I read this horrifying statistic. These two Australian sociologists figured out that I think it was 2012 or 2013, I can't remember. But in 2013, Australian scientists, researchers, spent an aggregate of 5 centuries writing grants. 5 centuries. Get that unit, centuries, right? And since fewer than 20% were funded, they basically wasted 4 centuries, right, of time. That's a lot of time down the tube, right? So that can't be the way to do it. This can't be a sensible way to do it. But I think in the end, finally, you kind of have to just increase the amount of money and recognize that you need to pay for failure. Was it Sidney Brenner? I'm sorry. Sidney Brenner is a famous molecular biologist. I talked to him one time, and we were talking about the grant thing, and he said, well, NIH grants have 2 parts. This will speak to what you said earlier. There's the first half of the grant are all the experiments you've already done, and the second half is all the experiments you're never going to do. And that's the way you get it funded, That's true. Sorry.
So you have talked about falsifiability and science, and the last slide is also talking about mistakes in discovery. Now we know examples where people do make mistakes, but it's a set of theories or a set of directions of research which is very hard to falsify. String theory. But nevertheless, somebody is paying for that kind of science. So, what's your take on that kind of science, which is doing well, and they're happy, but the others are. What do you
Well, I guess this speaks a little bit more to pluralism. So I'm not particularly a fan of the Popperian idea of falsifiability, except in limited way. I mean, I think you can use it in a limited way. It's an ongoing problem, how you tell good science from pseudoscience. I mean, you know, I could give you example after example of intelligent people making crucial mistakes about what's scientific or not. I mean, Steve Jobs, you know, had a form of pancreatic cancer that was curable like that. It's very rare to have a form of pancreatic cancer that's actually so easily curable with a minor surgery. He decided instead to use alternative diets and quacko medicine and stuff like that until he had a pancreatic cancer that killed him. Probably 2 decades or 3 decades before he did. I mean, he's not a dumb guy. And yet he could not somehow or other tell the difference between quackery and decent medicine. So there's always this problem. It's not a new one, but it's not a solved one yet either. There are many intelligent people that somehow still can't make this distinction. Maybe scientists in some cases too. So the falsifiability thing I don't think is a perfect way to go. It's just one stab at it, and it was a very good one. Otherwise, though, I mean, I'm not a historian of science, so I can only tell you what I've sort of been told by historians of science. But this is true of many areas of science. It's not so much that a hypothesis, you know, the story of Einstein and who did the solar eclipse? Eddington, right? I mean, this is, you know, okay, so in fact, that was Popper's favorite example was Einstein made this prediction and it could be falsified, but Eddington showed it to be correct. Whereas Freud, at the same time, was making all sorts of predictions about the ego, the id, and this and that, and whatever case came down the line, he could always form it into fitting in with Freudian theory. There was never any way to falsify it. But even there, I mean, relativity, there really was no, I think, at least as I understand the history of that science, there really was no single experiment that said, oh yeah, relativity, it's right. It's definitely right. It was a body of work that continued to be more or less correct, more or less in line with the ideas of relativity that built it up. I mean, I would say evolution is the same thing. I mean, there's no experiment you can do to falsify evolution. I can't think of one anyway. But there's a continuing body of findings that are consistent with it and that support it, and so you go with it for a while because it's productive. Now, I don't know about string theory because I'm not mathematically inclined enough or smart enough to follow it. But I would say you pursue string theory either because you haven't got a better idea or there's something productive that comes out of it, whether it turns out to be ultimately right or not. I mean, what's the difference? How close are we to ultimately anyway in anything? So whether it's ultimately right or not, I don't think it's anything to worry about. I think you pursue things that are interesting because they're interesting, potentially productive, and so forth. And I don't know if string theory fits that or not because I'm not in the field, but I would say there are plenty of things in other sciences that do. And many times we dismiss them too soon. So I would be hesitant to dismiss anything too quickly.
Yes, and then.
So you were talking about the difference between undergrad and graduate education, and so I was wondering, when we're teaching a 101 class or something like that, you have to cover a wide range of material, but maybe this is the last time they'll get science, and we would like to impart some of these principles so that they become good voters and good connoisseurs of media about science. What would you suggest that we can change in a meaningful way in our curriculum, given the time constraints that we have imposed upon us by outside factors in order to incorporate more of this?
Yes, so the key word you used there was the amount of stuff we have to cover, which is, I don't think I made this phrase up, but I use it a lot now anyway, the so-called tyranny of coverage, which seems to plague science courses more than any other area. And I'm not sure why. I'm not sure what we think we're gaining by this notion that we have to cover a lot of stuff, that we have to send off kids with a ton of facts about stuff that they're not going to remember them anyway. What's the difference? So clearly there are other things that would be. I mean, there's actually a whole series of very interesting books that came out of Harvard. One of your great presidents here, James B. Conan, who spent a lot of time convening committees and worrying about science in the general education curriculum, science for undergraduates, and in particular for non-science majors, for people for whom this will be their last direct encounter with scientists, by a scientist, something like that. And I think there are many suggestions. I mean, now, unfortunately, from the 1930s, 40s, early 50s, that are in these books, which you can get out of the library, and they're brilliant, and they have yet to be implemented. I mean, the notion of introducing narrative into science, the notion of introducing failure. We never teach failure. We never teach all the stuff that people got wrong for a while. And that's so critical. I mean, how do they finally find their way into the right answer, you know? How do they finally get through all that? Because it's really easy to have wrong answers for a long time. And they were there for a long time. Instead, we teach these heroic myths, you know, these arc of discovery bits of drivel, and they're not true, and they're not engaging is the worst of it. I think failures are much more engaging than a long list of successes by people that just seem a whole lot smarter than you all the time. Who wants to talk about that, you know? I mean, a lot of it was wrong for a long time, but wrong in really interesting ways. One of my favorite examples, just to go quickly, is in neuroscience, because that's a field I know. There was a legitimate science for a long time called phrenology, which we now think is, of course, a crock of shit. Right? And this was about bumps on your head. So in the middle 1800s, phrenology for about 30 years existed as a very legitimate science. People published on it, there were journals, there were experts, it was taught, and it was about bumps on your head, you know, and everybody has different sort of bumps on your head, and you could feel the bumps and say, oh, this guy's a criminal, and this guy's a, you know, charitable, this person is loving, this person is kind, this person's an ass, whatever it is. And all these different things, and these, you know, these heads, you've seen them, the maps of them and all the rest of that. I mean, frankly, we're doing fMRI today, and I'm not sure it's all that much different. You can read articles, and oh, this lights up over here, he's a criminal, get rid of that guy, you know, for sure, put him away. So, but phrenology, although totally and completely wrong in every scientific way, gave rise to two foundational ideas in modern neuroscience. It was the first time that people suggested that all behaviors and all emotions and thinking came from here. Not from your gut, not from your heart, not from your spleen, all these other places where various things supposedly emanated from. So it was the first time the brain was given this position of that's where thinking happens and that's where emotions happen. And the second thing was that things, certain activities, functions in the brain are localized. There are places in the brain where things are localized. Now, some things are distributed, but speech is localized here, and vision is back here, and hearing is over, things like that. And that was the first time those ideas came up, and they turn out to be correct. Now, where they place things and all that was not so much true. But to this day, you know, paleontologists and anthropologists still use skull casings and the bumps inside the skull casings to make lots of really interesting inferences about the kind of brains that early hominids had and chimpanzees and things like that, whether their amygdala was this big or that big, or the hippocampus was this big or that big. So here's phrenology, this totally bankrupt science, but it was foundational nonetheless. You know, you make the same case for alchemy and astrology, for that matter, as you know. I mean, a lot of early astronomy was basically astrology, right? And got better somehow. So anyway, I think those are the kind of things you can teach. And the more you engage students in that, then I think the more they'll actually want to learn about the other stuff. Because teaching them a bunch of science for dummy stuff, I just don't think gets you anywhere in the end. It's endless, and few people will be interested in it, but in general they won't. And they won't get a sense of what science is about, the great adventure that it is.
Have time for the last question, maybe?
Okay.
Sorry. I'm sorry, I could make shorter answers.
There's one other aspect of how we do science for real that the people you meet on airplanes are always surprised by when I say I'm going to flying off to use a telescope and say, oh, it's wonderful how you all get together and no, we don't. We compete like crazy for this time because it's a rare resource, and the aspect of competition of trying to beat the other person, having more than one set of people working on something is good. It's not a bureaucratic waste to have multiple teams. It's a necessary part of doing science. Now that's completely lost from the public discourse.
I mean that's a huge subject, so I promise I'm not going to go off on a long thing. But I think there's a sociologist of science named Harry Collins, who's English, who's written a couple of really interesting books on this issue. His interest is in expertise, what it means to have expertise in science, and there's levels of expertise. I mean, some members of the public become expert in this or that because they become interested in climate science or AIDS or this or that. But what do experts in a field know that other people do? It's this idea that I think the first person to think of it was a scientist named Michael Poliani. He was more of maybe an engineer. Anyway, he talked about tacit knowledge among scientists. So I'm only sort of circling around the competition issue, but that's what happens kind of in the inner circle of any field, is that there is competitiveness and yet collegiate, or one hopes a certain level of collegiality. I mean, there are always dicks, but you know, what can I say? But for the most part, I mean, what's great about science is that it's highly competitive and yet quite collegial. And we, you know, we're not perfectly open with everything, no, but we always can be, you know, drawn out, and with a couple of beers, you know, I'll pretty much spill the beans, because the subject, if the conversation gets interesting, and I've had a couple of beers, I tell them everything. What the hell, you know? And somebody once said, you know, when you close the lab door, you keep much more out than you ever keep in. So it never does you any good in the end, I think. So yeah, but that's very important, these issues. And I recommend Collins, but one of his books is called Are We All Experts Now? It's a very thin little book that has about, I don't know, more ideas per page than you could ever hope to pay for. So I recommend it highly. It's an interesting book.
What's it
And
called?
discusses that.
What's the book called again?
It's called Are We All Scientific Experts Now? By Harry Collins. And then you can find other books by him too. He's a fairly popular writer. Although he's a very well-regarded sociologist, and mostly of physics. He studied people who studied gravitational waves, was his particular area of interest, and he spent lots and lots of time hanging out with groups of people that studied gravitational waves and trying to understand what it meant to be an expert in that as opposed to an interested lay person, as it were. And it's quite interesting, actually.
All right, I'm afraid we need to stop the conversation, but Stuart is going to be here today and tomorrow, and there are still a few spots available if you want to spend some time with him. And please let me know if you went to junk for dinner tonight. And thank you so much for your time.
Thank you all. Thank you all very much. Great conversation.